Now we go to the second and third factor in fluorescence intensity, i.e. temperature and solvent. Okay, what happens when you heat molecules up? Okay, they will collide. They will collide with each other because of the heat given, and therefore it will increase the collision frequency. What happens when they collide each other? At that point, fluorescence will decrease. Okay, fluorescence will decrease with increasing temperature. Why? Because the increasing external conversion inside the Jablonski diagram. So remember back the Jablonski diagram at longer wavelength, we have phosphorescent region over here, whereby it tend to emit radiationless non-activated radiation, and therefore you will lose the fluorescence intensity that's supposed to be here. Okay, it will be external over here. So please bear in mind, when you are working in your PSM later or when you are working outside, you have to make sure when you are preparing sample standard solution for fluorescence analysis, make sure that the room temperature is okay. It's not varying each hour. Okay, means that you have to look on the air conditioning system, and also make sure that heating is not involved in preparing the solution, because you will decrease the fluorescence significantly. Okay, next we go to solvent viscosity. Decreasing solvent viscosity, okay, decreasing solvent viscosity will increase external conversion, therefore your fluorescence will be lower. Okay, lower viscosity will lower down your fluorescence. Okay, for example, between heptane, okay, pentane and heptane, which one is more viscous? Okay, the one that is having more carbon inside it, okay, will be more viscous. Okay, therefore in this case heptane is better solvent as compared to pentane. So does for octane. Okay, octane or nonane. So octane is better solvent. And then if you are using solvent that have heavy atom inside it, okay, the one from group 17, such as iodine, it will also give a marked effect on the fluorescence. Okay, when you have this kind of heavy atom, what will happen? It will create intersystem crossing, whereby it will go towards phosphorescent. Okay, intersystem crossing dia pergi ke sini. Okay, it goes into the triplet state. Okay, increasing phosphorescence. So when you have a halogen substituent inside your solvent, or even inside your inside your compound, okay, it will reduce the fluorescent quantum yield significantly. Okay, you see that as compared to naphthalene with iodonaphthalene, it reduced by at least 1000 times. Okay, in terms of fluorescent intensity quantum yield, but it promotes your phosphorescence. You see that the phosphorescence is increasing. So if you have iodonaphthalene as your compound, as your analyte, you better use phosphorescent mode rather than fluorescent. Okay, because there's no point on detecting using fluorescence spectroscopy due to the low fluorescent intensity that you will get. Okay, so internal heavy atom effect will promote internal system crossing. Now we go into effect of pH. Molecules with acid-base active substituent, okay, amine, hydroxyl, carboxylic acid part, because they are easily deprotonated or protonated, okay, they will be in the form of charge in a certain medium of solution. Okay, because it is prone to be changing in pH. Okay, it can also promote resonant form because of the charge effect of pH from the medium that affect the charge. When more resonance are possible, its excited state can be greatly stabilized. Means that this stable je in Jablonski diagram, means it from the second singlet state as compared to the first singlet state. Okay, it goes up from the ground state, it get excited, and it is stable over here. It will not go to the first singlet state easily to release the fluorescent, okay, because of the resonance form. Okay, now let's go and see how aniline exhibit better fluorescence as compared to anilinium ion. Okay, so the same thing with what oxochrome and chromophore situation. So NH2 is oxochrome. It is an auxiliary functional group that can enhance the absorption. But when it is charged, it is stabilizing the excited state, which is not promoting it to be into the second singlet state that will produce fluorescence. Now let's go on the resonance form of aniline. You see that the lone pair electron, when it is, for example, in a medium of acidic, okay, acidic medium, acidic medium tend to protonate, okay, tend to protonate aniline, okay, means that dia bagi extra H lah, extra hydrogen, okay, extra proton. So when it starts to give extra proton, okay, it start to resonate. Okay, I hope I still remember my organic chemistry. Okay, it start to resonate from here, okay, and then here, and then it will go to this part over here and producing the N plus for having extra proton. So we have anilinium ion, okay, which is stabilizing the excited state, reducing the fluorescence. Then we go into the next factor about quenching. Quenching is a process by which molecules in the excited state lose energy to other species. Okay, they lose energy to other species without fluorescing, means some sort of radiationless loss of energy. Okay, this is happening when you are having a very concentrated sample. Okay, analyte very concentrated, whereby they collide more. What happens when they collide more at higher temperature, higher concentration? They will have conversion. Conversion will reduce the fluorescence radiation. Okay, so when you want to have high fluorescence, okay, work at low concentration rather than at higher concentration. Therefore, we can summarize over here factors that can enhance fluorescence is when you have more pi interaction from ground state to excited state, and as compared to the N to pi star over here. And then the second part is that low intersystem crossing yang daripada fluorescent to phosphorescent. So if you reduce this one, you will have fluorescence, because fluorescence is inversely proportional to phosphorescent. And then if you have a rigid compound, is even better, because it will reduce internal conversion over here. Okay, aromaticity. Low temperature will help you to get good fluorescence, and non-polar solvent at lower viscosity will also help. And then we go to factors that is not good for fluorescent. The most important is that, okay, you have to mediate the pH of the solution. Okay, this is true for analyzing, for example, vitamin B. I think vitamin B is riboflavin. They fluoresce. And vitamin B is easily altered by pH. Okay, when you prepare in a wrong pH solution, fluorescence is suppressed significantly. And then if you have a halogenated species in your fluorophore or even in your solvent, it will reduce your fluorescence due to the enhanced intersystem crossing. Again, intersystem crossing from fluorescence to phosphorescence.